today I'm going to be doing more problems on SN1 and SN2 only. I'm not really going to be talking about E1 and E2 here, just doing these practice problems based on the SN1 versus SN2 and what the products they're really going to make, and I'll draw the mechanisms wherever it's necessary. So let's look at this first example. So in the first example, the very first thing you want to do is be able to identify your alkyl halide and your nucleophile. So this particular alkyl halide that you have here is actually going to be a primary alkyl halide. So that carbon right there has only one other carbon attached. So it's going to be in a primary. So if you have a primary alkyl halide, they would only do an SN2 type reaction. They're not going to do an SN1 reaction. And that helps by this nucleophile that we got, because this nuke is relatively strong. So this, when I go ahead and separate this out, obviously this sulfur and potassium, since it's an ionic bond, is going to have a full negative charge. Potassium is going to have a full positive charge here. So since this is an SN2, I can have this backside attack being taken place here, and we would have this leave. Okay, and let's just go ahead and draw how the product's going to look like. So we want to go ahead and have this bond broken, and I want to make sure I make a new bond right there, and then we're going to have the sulfur, and we got this cyclohexyl group on here. Now this SN2 involves an inversion in stereochemistry, but that carbon is not really chiral, so you don't have to really worry about how the stereochemistry is going to look like. So that's going to be the product. Along with that, the side product would be just the KBr. You may not have to worry too much about it, but this is how it's going to look like. Let's look at this next one, and this next one, first to identify the type of alkyl halide, we have a secondary alkyl halide, and the secondaries can do an SN1 and an SN2, both of those. And you just got to worry about out of those two, which one will work here. And then I want to look at my nucleophile. So your nucleophile, since it's an KCN, and if I go ahead and break that into ions, since it's an ionic compound, we are looking at Cn minus as our nucleophile. That's in a strong nucleophile, and since it's a strong nucleophile, and on the top of that, we're using an aprotic solvents here. This is going to do an SN2 mechanism. So this involves an inversion of stereochemistry. Now, if you look here, this compound that we got has your chlorine pointed down in the chair conformation. So when I'm drawing this in the two-dimensional form, this chlorine will be going back in the page. And then when I'm using my nucleophile to do the attack here, it's going to do a backside attack. And when it does the backside attack, this would leave. And since it has done a backside attack, you're going to have an inversion in stereochemistry. So maybe first I want to go ahead and draw the two-dimensional form of it, and then I'll worry about drawing it into the chair form. So I want to go ahead and get that coming out of the page now, and I would have the CN here as my nucleophile attached there. And along the side, you're going to be making an KCl. Now, I want to go ahead and make sure I go back and convert it to a chair conformation. And in order for this to be converted into a chair conformation, I can probably just go ahead and copy my starting material. And now you can clearly see how this chlorine or the CN is actually coming out of the page, so that needs to be pointed up. So when I draw this on this particular chair, this is going to be pointed up like this one. Now this may not be the most stable one because this is coming out of the page, so I want to actually draw the most stable one. And to draw the most stable one, I can go ahead and flip this chair, and when I flip this chair, I would have this in the inverted form. So this is how the inverted form is going to look like. So if this was 1 right there, when you invert it, this becomes 1 right here. And then your axial will turn into an equatorial. So this is where you're going to have the CN. So this would be the more stable conformation. So this is how you really want to draw it. As long as you draw this pointed up and in the equatorial, that's probably what matters the most in this particular case. Okay, moving along, we have, again, this is going to be your secondary alkyl halide, And we're using acetylide here. So remember, acetylides usually have a negative charge on the carbon, so that's in a strong nucleophile and a strong base. And this could very well do an E2 mechanism as well. So I'll just go and write that down like you can do an SN2 and an E2 here. But since we're only worrying about the SN or the SN1 versus SN2, we're not really worrying about the E1 and E2. So we're only going to be doing an SN2 for this particular case. So since we have this doing an SN2, I would have this doing the backside attack. And when this does the backside attack here, this chlorine is going to leave. And how is your product's going to look like? We will have this in the inverted form. So we would have this going back in the page, and you would still have the carbon or an acetylide group here, or acetylene there. And then along with that, we just have the Cl minus there. That's just going to hang out in the solution. So like I said, remember it's probably going to do an E2 as well, because that's probably going to be major over the SN2. But since we're only talking about the SNs here, not the eliminations among SN1 and SN2, it will do an SN2 here. Okay, let's look at this next one here. We got the same reactant, same alkyl halide that's in a secondary. When I'm looking at my nucleophile, this does not have any negative charge anywhere, so this is a weak nucleophile. So since this is a weak nucleophile, and this very well could be acting as your solvent as well. So this is going to be an aprotic solvent, and due to that, this will strictly going to do an SN1. It's not going to do an SN2. So in terms of mechanism, the way the SN really works, we would have a loss of leaving group first. So I'm going to go ahead and get rid of that leaving group. And when I get rid of that leaving group, we make a carbocation. So I'm going to go ahead and make a carbocation there with a positive charge. And you would have the Cl minus along the line here. And now, in the next step, I could have this CH3OH coming in and doing the nucleophilic attack. So when it does the nucleophilic attack, this carbon right here is an sp2 carbon, so it's in a planar structure. So it can do in a top attack or bottom attack. So you could possibly have this OH or the OCH3 group attached at the end of the day, either coming out of the page or going back in the page. So I'll just kind of draw that going one way in the mechanism, and we will draw both of the products at the end of the day. So I'm going to go ahead and make sure I have this right here. Space coming out of the page because that's the chiral center. And I want to keep the rest of the stuff here. So that's an H and that's an OCH3 with a positive charge. And I want to make sure I get this proton taken care of. And in order to retrieve that proton, I can use any of the bases or any of the conjugate bases I got here in the solution. And I could very well use this chloride. And in realistic, you actually do the workup with a weak base to get rid of that proton, or maybe with water. But right now, in the mechanism, I can just kind of show that this chloride is going to be the one that's grabbing this proton, and it's going to restoring the electron density back on here. So then what you get is this product here. And along with that, you're going to have an HCl. And just like I have said earlier, that this could have done the attack coming or going into the page. So you would have a pair of enantiomers where this bond will be going back in the page. So you get a pair of enantiomers, or you can say that you get a pair of racemic mixtures for this particular O1 here. Okay, moving along, in the next one we see this is going to be in a secondary that's in a weak nucleophile, and since it's a weak nucleophile, it's going to do an SN1 again. It's not going to do an SN2. And when we do the mechanism, the first step would be the loss of this iodine here. When we lose this iodine, we would have a carbocation made right here. And I want to go ahead and write down the iodine right here. But then this carbocation that you have made, it's actually a secondary, but if I can somehow move this positive charge onto the left carbon right there, that's going to be in a secondary, and along with that, it's going to be in a benzylic. So I want to go ahead and actually do that. So in order to do that, I'll move one of the hydrogens that attached to that particular benzylic carbon onto this side right here, and we'll call that a 1,2 hydride shift. And obviously, you always want to look for a more stable carbocation anytime you are going through the mechanism of carbocation formation. So when that happens, that hydrogen moves to the right side or right carbon. I'm not really going to draw that because it's just a skeleton. And that positive charge moves on to the benzylic position. So now this is more stable because it's a secondary and it's in a benzylic. So that's going to be a more stable carbocation. Now I want to go ahead and get my get my nucleophile, which is this guy right here. And this nucleophile again is going to be able to do either the top attack or bottom attack. Um, so when it does the top attack and bottom attack, you have a possibility of getting a pair of enantiomers there. Okay, so let's see what that's going to look like. Suppose this is right here. I'm going to draw the mechanism with one of them only. So let's suppose this is coming out of the page. And we would have the OH here. And we would have the positive charge on that oxygen there. So what I want to do is go ahead and use iodine, the iodide rather, to remove this proton or do an acid-base reaction here. And you can very well do this reaction in a reversible form. So that's okay as well to have a reversible arrows there. And then you will end up making this as your final product. Maybe I can make that a little bit smaller. And then along with that, you're going to have an HI. But remember that was done the top attack. You also have the possibility of doing a bottom attack. And when you do the bottom attack, you would make this bond going back in the page. So you have a potential of making a pair of enantiomers in this particular case, or you can say racemic mixtures. This is what typically happens whenever you run an SN1 mechanism. Let's try this next one. It might be a good idea if you guys try it and see if it matches with what I have here. And it seems like we have this aqueous NaOH, and just water is used to dissolve this, but you have a lot of hydroxide here. So OH minus that we are using here, that's going to be your strong nucleophile and a strong base in there. But since this is in a secondary alkyl halide, so that's your secondary alkyl halide, this can do both an elimination and a substitution. So SN2 and E2 are possible, but I want to just go ahead and say that we're only going to be worrying about the SN2 here. We're not going to be worrying about the E2. And when it does that, we're going to be doing this backside attack. So this backside attack right here. So this right here, this bromine is kind of coming out of the page right now. So when you attach this OH group, it's going to be going back in the page. So to make that go back in the page on the chair conformation, it will be pointed down in that particular case. So you could have possibility of OH kind of shown like this one. So you want to make sure you have the stereochemistry inverted in that particular case. And along with that, you're going to be making an NABR. If you look at this next one particularly, the really difference you have in the previous one and this next one is this is still in a secondary, but when I'm looking at the nucleophile, it's not really in a strong nucleophile anymore, but rather it's a weak nucleophile. And since it's a weak nucleophile, it's not going to do an SN2, but rather it will do an SN1. So then how would your product really going to look like? That is going to differ. So mechanistically, first of all, you would lose that bromine. I'm going to go ahead and lose that bromine here. And we make this carbocation here. And you can certainly do this with the drawing a two-dimensional form of cyclohexane, but you can very well just do it with this here as well. So when you use, obviously you have the bromine lost there. or the bromide lost there. When you do in the next, use the next step, water as your nucleophile, this has the potential to do either the top attack and bottom attack. So you would be able to go ahead and do the attack like this, or you can do the attack the other way around. So in that particular case, this OH that's going to be attached to it, it could very well be coming out of the page or going back in the page. So if it's going back in the page, it will be pointed down. So I'll just show the mechanism with only one of them. And in that particular case, I want to go ahead. The last step would be using the bromide here that you have retrieved to do the acid-base reaction here. And you can very well have this reaction in a reversible form. Restore the electron density back onto the oxygen. So this is how your products is going to look like. So we have the OH in this particular case going back in the page. And then if I want to draw my second product, obviously you said it can do in a top attack and bottom attack. So when it does the top attack, you would very well have the OH going out of the page or coming out of the page, and that would be pointed up. In the previous case, it was going down or going back in the page, so it has to be pointed down in the chair conformation. And if it's coming out of the page, it has to be pointed up on the chair conformation. So what's really the relation between those two compounds? They're not really enantiomers of one another because it's not really chiral, but you're not really changing the position of this equatorial metal. So there's no chirality, but they're kind of cis and trans of one another. I can say this in the second one, the OH and this metal, they're both pointed down. So that's like an cis form. And when you're looking at the second one here, this OH and this metal group, they are opposite to one another. So that's in a trans form. So what would I really call those? You can call those in a pair of diastereomers in that case. So you could very well see the pair of diastereomers in SN1 reactions anytime you have more than one chiral centers, or in this particular case, if you have a cis or trans being formed in there. Well, we look at this next one, that's in a primary alkyl halide. And since this is a primary alkyl halide, it's only going to do an SN2 type mechanism. The only thing that you really have here is the H minus that you're actually getting from the NaH. That H minus hydride is actually a base, is not in a nucleophile. So what it's really going to do is it would first grab this proton here. So we can draw that here. It's going to grab that proton from the alcohol. So when it grabs this proton from the alcohol, it would put the negative charge on that oxygen that would make that as a nucleophile. So you lose the H2. So you do an acid-base reaction first, and then you make this guy right here with a negative charge on the oxygen now. So this oxygen has the potential to act as a nucleophile and is going to close the ring on its own. So you have the nucleophile and you have this electrophilic position at the same molecule, and then this comes out, and then you want to make sure you are able to count how many carbons you really have in this ring that you're about to make. So I can call this to be 1, 2, 3, 4, and 5. So it's going to be a 5-membered ring. So I can go ahead and draw a 5-membered ring here. But remember, one of the positions is taken up by the oxygen. So I want to go ahead and draw the oxygen right there, and that's pretty much you really gonna have it here. I can, if I want, I can go ahead and count this as 1, 2, 3, 4, and 5. So that's gonna be your final product, along with, you can say you would have the NABR formed here, and obviously you have the hydrogen gas retrieved in the beginning because you did an acid-base reaction. So that was an SN2 mechanism. It did in a backside attack, and it had in backside attack, but it wasn't a chiral center, so I don't have to worry too much about the stereochemistry. When I'm looking at this next one, what we really got going on, this is going to be in a tertiary alkyl halide, and the Na and a 3. So N3 typically have a minus sign on here. So that's in a strong nucleophile, but remember that's in a tertiary alkyl halide, so this is only going to be doing an SN1 mechanism because tertiaries don't do SN2. So since I'm doing an SN1, the first step involves the loss of leaving group. When I lose this leaving group, would be making a carbocation, and that carbocation is very well going to be a tertiary carbocation. So you already have the most stable carbocation. Now this carbon right here that's bearing the positive charge is in turn attached to two other methyl groups. So it's not really chiral. So I don't really have to worry about doing the tag into the page or out of the page. I can just go ahead and have this N3 doing the tag, like right here, and we will end up making, just copy that down here, we will have this N3 attached to it, basically. So that's a formation of an azide bond that you will eventually see at some point. So that was an SN1 mechanism. Let's look at this next one here. We got an benzylic position. It's gonna be an OMS that you see right here. It's a good leaving group, so you can just treat this like an halogen here because they are also good leaving groups, another form of it. And since it's in a benzylic, you can also do an SN1 and SN2, but what we really got going on, in addition to this being in a benzylic, this CH3O minus, that's actually in a strong nucleophile and a strong base. So it can do an SN2 and an E2, but it does not really have any carbon, any beta carbon with an hydrogen. So there's no hydrogen here on that carbon, and there's no carbon on this side. So it's not really going to do an elimination. It's only forced to do an SN2 mechanism in here. So when I'm doing the SN2 mechanism, I want to go ahead and do the backside attack. So when I do the backside attack, this is going to leave. I want to make sure I have the stereochemistry inverted. That's the whole point when you're doing the backside attack. So D is a form of a heavier isotope of hydrogen, so it's going to be deuterium. That's the only difference. And this right here is going to be a new bond that's going to be made, and we're going to have the O CH3 there. And along with that, we will have this OMS that's going to be your good leaving group that's going to be hanging out, and it's going to be accompanied by this Na+. Now, to have this stereochemistry inverted, I want to make sure I have the R converted to S or S converted to R and so on. So when I'm trying to figure out how this is going to look like, I know there is a hydrogen that's going back in the page. So that would be 4, this would be 1, that would be 2, that's 3. So this is an R, and I want to make sure this turns out to be an S. And one of the best ways to make this S, I can have this deuterium go back in the page. So when I push this back in the page, that means your hydrogen is coming out of the page. So that would be 4, that would be 1, 2, 3. So right now it kind of seems like it's going clockwise, but then you would have to flip it because your lowest priority group is coming out of the page. So that is actually going to be an S configuration. So make sure you do an inverted stereochemistry in this particular case. Now, this next example is actually similar, but instead of using this strong nucleophile, I have a relatively weaker nucleophile. So since it's a weak nucleophile, I'm only going to be able to do an SN1 mechanism here. So the SN1 mechanism involves the loss of leaving group first. So I'm going to go ahead and have this tosylate group lost. So OTS is another good leaving group, just like an OMS. So you can treat this similar to an halogen here. So I would first create this benzylic carbocation, which we know it's relatively stable. And once you create the benzylic carbocation, it loses the chirality, so I can just go ahead and draw the D right there. So this would have a positive charge. But remember, this is about to make a chiral center because you have a deuterium and a hydrogen attached and this big ring on the left side. But when I'm getting this methanol coming in and doing the top attack and bottom attack, it has the potential of doing both of those. So you will eventually make a pair of racemic mixtures. So I'll show the mechanism with only one of them. So I could very well have, suppose this is my new bond right there, and you're gonna have the O, H there, and a CH3. So this gets a positive charge, and we still have this deuterium. Let's say this deuterium is coming out of the page now, and I want to go ahead and doing a basic acid-base reaction where I could use probably the tosylate here mechanistically to grab this proton. And when this grabs the proton, it kills the positive charge on here, so we will end up getting this stuff right there. So maybe I can draw that going up here now. So that's one of your products that you're going to be making. Then your other product that you're going to have, since you're doing an SN2 type reaction here, SN1 type reaction, so you will be seeing the racemic mixture of the enantiomers there. To make the other enantiomer, all I can do is just go ahead and have this go back in the page. So this deuterium will be going back in the page. So you get both R and S in this particular case. So that was really the difference between the previous reaction and that reaction. So they're both able, both of these alkyl halides are able to do SN2 and SN1, and it really depends on what type of solvent system or what type of nucleophile you're really using. And even in the previous one, since you were using acetone as your solvent, acetone is an aperiodic solvent and it prefers an SN2. And on the top of that, you had a strong nucleophile, and that will do an SN2 mechanism instead of SN1. Okay, this next one I have here, that's in a secondary. So we're given a Fischer projection, so that's in a secondary alkyl halide. And when I'm looking at my nucleophile, that's an SH minus, so that's your strong nucleophile. And since it's a strong nucleophile, it will do an SN2 mechanism, and it will be doing in a backside attack. And when I want to go ahead and draw this in the product, I want to make sure I have the inverted stereochemistry. That's the whole point. And one of the ways to have the inverted stereochemistry is just have this drawn, the position of your S, and the hydrogen will be flipped in that case. And if it becomes harder, you can always try to figure out RNS, and you need to draw the other form in the product. So I want to go ahead and have the hydrogen here, and I want to have the SH there so that I can have the inverted stereochemistry on this particular one. And this, along with that, it's going to make an NaCl. All right, so on this next one here, kind of same story, still Fischer projections. I have this carbon right here is technically isn't a tertiary carbon, right? So I can't really say this is gonna do an SN2, even though you have a relatively stronger nucleophile. But this is still gonna do an SN1 because your tertiaries don't really do SN2 mechanism. So when I'm making the products, obviously this is gonna involve the loss of nucleophile first, and then we're gonna have the CN minus doing the attack there, this going away. So you lose the chloride here first in SN1 mechanism. And when I draw, duplicate that here, I want to make sure, okay, keep everything else the same. So this is still hydrogen there, and there's still a methyl group right here. I would lose, so you would still have technically the methyl group here, so you have the positive charge. So when your CN minus comes in, it can do the top attack and bottom attack, which is just like you would do normally. So when it does the top attack and bottom attack, it would have the possibility of having the CN either onto the left side or onto the right side. So maybe I can just draw this right here. Keeping everything else to be the same, I can have very well the CN onto this side. So that's one of your products. And then I can also have the CN on the other side. That would be your other product. So get rid of that. So I have a CN here. Let me just change. So those are the two products you're going to be making. And if someone asks you what is really the relation between those two, they're not really enantiomers of one another, because even though you're flipping the position on the top so that chiral center gets flipped, but when you look at the bottom one, that doesn't really change. So they're not mirror images of one another. They're not going to be enantiomers, but rather they're going to be pair of diastereomers. So just because you're doing an SN1 mechanism, that does not mean you're always going to have a racemic mixture or a pair of enantiomers. Sometimes you may get diastereomers, just like in this particular case. And obviously, if I want to look at what my side product is going to be, that would be just NaCl in this particular case. Now, finally, this last reaction I have here, kind of similar. I got this tertiary alkyl halide, and that's going to be your methanol. That's going to be your weak nucleophile. So this has to do an SN1 mechanism. So I want to go ahead and first get rid of this chloride here. That would be your first step in SN1, the loss of leaving group, and that makes the carbocation. So this makes a carbocation here. And this carbocation is actually tertiary, but the problem with that is there is a lot of ring strain in this one because four-membered rings are not really uh, stable. So you can have a ring opening here. So ring opening rearrangement. So what really happens when you're opening the ring is I can have this bond to be broken and it would go right here. It will connect to the next one, another way of saying. So when I go ahead to retrieve or to release the strain, maybe make a five-membered ring. So when I'm making a five-membered ring, let's count this as 1, 2, 3, 4, 5, and 6. So I'm just counting it for my own convenience, not according to the IUPAC um, numbering system. So this would actually make a five-membered ring now. So let me just go ahead and draw the five-membered ring. And I can still go ahead and count it from here. So that would be 1, 2, 3, 4, and 5. And then your sixth one is going to be connected to the fifth, obviously. Now, where is going to be your positive charge if you think about it? Your positive charge initially will get onto the fourth carbon because if you think about it, you have this carbon or this bond was broken and this one still makes the bond with the fifth carbon, but then this four becomes an electron deficient and it will have a positive charge on here. But then you can still do an electron carbocation rearrangement on this because that's in a secondary carbocation, and you can very well make this as a tertiary carbocation if you can shift this to the fifth carbon. Now, this is very unlikely to happen where you're actually doing two shifts together, like first ring opening and then do a 1,2 hydride shift. But theoretically speaking, it's still possible because that's not really most stable carbocation. It's less stable carbocation, and if you do the hydride shift here, it can still have the carbocation on the most stable carbon or the tertiary carbon. So it still have a possibility of doing it. So now I'll erase everything else. The positive charge moves onto that carbon, and I'm not really going to draw the hydrogens. And then eventually you want to do the next step will be the OCH3OH, doing the top attack and bottom attack, but it doesn't really matter in this particular case because that's not chiral. So I can just draw it only one way. So I can have this right there coming in with a positive charge. One is hydrogen. Oops, not two charges. And then finally, I can go ahead and use my chloride to get this positive charge out, or get this proton retrieved. So that would be your final product. So there actually two things happened here. You did open the ring because there was a lot of ring strain on this ring, four-membered ring. And even though when you open the ring, you first made a positive charge on the secondary carbon, so that was a secondary carbocation, and you did this hydride shift to make this a tertiary carbocation. And you may very well get some product that's going to be coming from the secondary carbocation as well. But if I theoretically speaking, I want to make the most stable one, I want to still go ahead and do the hydride shift here to make the most stable product, most stable carbocation, and eventually this product here.